It's teaching chemistry through memes. Yeah, so this is you've seen this meme where they're like one shooting the other or whatever. So Lewis thought the Vesper theory is replacing it. Valence bond theory is where Vesper theory comes from, and then MO theory is up in the balcony. He's in the balcony looking at all the three in front of him. And then this is atomic orbitals. Like each atomic orbital says, these are my electrons. But then with molecular orbitals, these are our. This is a little kind of shared everything. So it's kind of funny. So that's what we're going to do. We're going to do a little review of the molecular orbital theory because, again, it's good to review before we get into the ethene molecular orbital diagram. So this is, we'll also highlight the difference between local bond theory and molecular orbital theory because they're totally different theories, totally different. So we'll learn that today for sure. And then we take that Lewis dot structure, we do the valence shell electron pair repulsion theory, which means that wherever the electron domains are, they get as far apart as possible. So like in formaldehyde, carbon's double bonded to oxygen and it has two single bonds to the two hydrogens. That's 3 electron domains, even though there's 4 electrons in the double bond and there's 2 electrons in the CH bonds, they still count as 3 domains. And so around that carbon, listen carefully, around that carbon, we have an electronic structure of trigonal planar. So that's the electronic structure around the carbon atom. The structure of the whole molecule is, there isn't a name for it, right? It's just formaldehyde. It is C2V if you go through the character table, but we talk about the electronic structure around particular atoms in valence shell repulsion theory. Remember that whole big deal I made about some students calling water tetrahedral? Yeah, the electron domains around oxygen are tetrahedral, but water is bent. The molecular structure is bent. But anyway, that's so that we get the hybridization orbitals from these electron domains, depending upon how many domains there are. If there's 2 domains, it's sp. 3 domains, it's sp2. If there's 4 domains, it's sp3. And then if it's 5, we have to bring in the d orbitals. We don't see those on group 2. Period 2, with the carbon, nitrogen, oxygen, and fluorine. Like we don't see nitrogen pentafluoride, where we would have 5 domains around nitrogen. But we do see phosphorus pentachloride. So then we need 5 electron domains. And so we have, let's see, S, 3 P's, and a D. So we pull those 3 d orbitals down. It doesn't look like phosphorus has d orbitals because we know that's the d block. But because of the Aufbau filling scheme, the 3 d orbitals start with scandium. So the period 3, of which phosphorus is a member, there are 3 d orbitals, and they're very close in energy to the p orbitals. So it can put electrons into that d orbital, and there will be a rearrangement of the electron cloud, and then we call that hybridization. And then if we got to sulfur, we could do SF6, and that would be 6 domains, and that's sp3d2. I've run out of fingers then, so sp3d2. Okay, so there's our 6 domains. Now that's what we've used this whole time to build our molecules to go through the flow chart, right? Everybody's comfortable with that. So this is how we make our molecules and draw our initial guesses, and this is what Gaussian's using in the builder in Gauss View. So when you go and pick the atom and the atom type, you have choices of sp3 and spd2. They're not labeled that way, but that's what you see. And notice on period 2 for carbon and nitrogen and so on, you don't have the sp3ds and all of that. But if you go to the 3rd row, you'll see more options. If you pick a phosphorus, then you'll have this sp3d option for the type of phosphorus that you're picking. So that's all local bond theory. So what does the local word mean when we say local for local bond theory?
Just what is in the area of what we're looking at?
Yeah, but there's a specific what? The what? Localization of what? No, but close. It's related to charge. Yeah. And so they're saying that the electrons are local to each bond. So the carbon-hydrogen bond has 2 electrons that are assigned to that bond. They're local to that bond. And the carbon, oxygen, and a formaldehyde have 2 sigma electrons that are local to that bond, and 2 electrons that are in the pi bond. And then you have the non-bonded pairs that are on that oxygen. And then you have the other carbon-hydrogen bond. You have 2 electrons assigned to that bond. So the electrons are local to each bond. Okay, so that's what local bond theory means. And then we have molecular orbital theory. This, I remember being a freshman, reading about this in Chem 1 and not understanding it. And this is one of the greatest memories of my life because it really enforced the one way of learning, okay, brute force. I'm reading this paragraph on molecular orbital theory and I didn't understand it. So I read it again and I didn't understand it. I read it a third time. I didn't understand it, right? And then when I'm reading it the fourth or fifth, however long it took, the word molecular jumped off the page. It's not local. It's a molecular orbital. It's not an atomic orbital. It's a molecular orbital. These orbitals go over the whole molecule, not the atom and not the bond. Okay, so that's the thing I want to emphasize. So and we'll talk more about this. The molecular orbital theory is confirmed with UV and X-ray data. And we'll do today simple MO theory for diatomics, and then we'll get into some complicated MO theory near the end with the FE. So we'll go through the basics of MO pretty quickly. We're just going to jump right into the diatomics. So here's the molecular orbital diagram for fluorine. So when you typically make a molecular orbital diagram, you start with, I guess you could start either way, but you could put the molecule here in the middle, F bonded to F, and then over here you have the atom on the left and you have the atom on the right, and you have the atomic orbitals over here, atom and molecule. So the molecular orbitals are in the middle and the atomic orbitals are on the sides. So this is a MO diagram. And we can see all of the pictures. You have the 2s and the 2p atomic orbitals. They come together and make molecular orbitals. And you can see the linear, So what is the acronym? What are the letters? Linear combination of atomic orbitals. Linear combination of atomic orbitals. Yeah. Oh yeah. And these are symmetry adapted. So we could put an SA in front. Symmetry adapted linear combination of atomic orbitals. So we come up with these by symmetry. So we could run through the character table and come up with all of these combinations, and we would get their symmetries, and we'll have symmetries later. Okay. So this one is A1G, and we could write the little shorthand of this is the 2s on atom A plus the 2s on atom B. You see they have the same sign down here. And then we could do the A1U, that's the 2s on atom A minus the 2s on atom B. And here's the A1G. And so this, I went ahead and put a plus sign here, even though they're like the plus and minus has switched on that, because I wanted the plus ones to be with no nodes or fewer nodes than the minus ones. So this is the 2ZA, 2PZ on atom A, and the 2PZ on atom B. Why the Z axis? Well, that's the symmetry axis, right? This has a C infinity axis along the Z direction. So this is the Z axis of the molecule. So these are 2PZs. Okay. And it doesn't really matter which one of these, but these are the 2PXs and PYs later on. But let's look at the opposite combination of the 2PZs. So 2PZ on atom A minus the 2PZ on atom B. That would also be an A1U. And those are those right there. Now we define these as sigma bonds because they have a +1 under this rotation. So this rotation is C infinity. The characters for these are all +1. Can you see that? If we rotate those orbitals, then there's no change in the deflection of the wave functions, the pluses and the minuses. Okay. Okay, but then we have the E combinations, the X and Y combinations. So this is 2px on atom A plus 2px on atom B, or the YA plus YB. And then here's the minus combinations. And this is E1G, the 2px on atom A minus Y. So these are, here's, you've got an extra node here, so that's breaking the bond. Okay, here they both have nodes that contain the bond and the pi interactions. That's why we call it side on. So those p orbitals come together on the side and they delocalize or have a node. And so look at the star and the non-starred orbitals. So here's a star, okay, and notice that the node breaks the bond. Okay. We can calculate the bond order. Let's finish this. So here's a star here, and you see that node breaks the bond. Here's a star here, and you see there's a node that breaks the bond. So these are where the F atoms are. So the space between them is the bond. Does that make sense? So we call those anti-bonding orbitals. The other ones are bonding orbitals because there's electron density between the atoms. See, if I have an F atom here and an F atom here, and I've got all this electron density in between, that's going to hold those atoms together. So that's a good thing. And so we could calculate the bond order, just BO up here in the corner. And it's the number of bonding electrons minus the number of anti-bonding electrons. And I think that's a fill-in for you guys in the notes. So it's blank, so you can fill it in. So let's count up the bonding electrons. So we have, you know, these right here and these right here. So this is 2, 4, 6, 8. So that's where the 8 came from. And then how many anti-bonding electrons do we have? We have this one here, these, and this we have 6. 2, 4, 6 anti-bonding electrons. Why do we divide by 2? Because it takes 2 electrons to make a bond. So we're just trying to count up how many bonding electrons we have versus the anti-bonding. And so when we divide by 2, we end up with a bond order of 1. So that is that the fluorine-fluorine bond is a single bond. So this is a way to get to how many bonds you have that has nothing to do with the octet rule or anything that, like the Lewis dot rules that we have. This is a different way of calculating that bond. So that's the diatomic molecular orbital with p orbitals. Let's pause for any kind of clarification because it's going to get complicated fast. So make sure you understand every piece of this. Yes. The pi and the sigma, or the 2 plus and 2 minus. This right here, E1G and E1U. Okay, so these would come from the projection operator. If we go through the character table, and we did like the orbital on atom A, and we did a reflection and an inversion and a rotation and all of that, the plus ones and minus ones, as we went through that row on E1U, would end up with this right here. Okay, it would end up with this net result of the 2py on atom A plus the 2py on atom B. And so if we draw those, this is what they look like, and then they have this overlap where I really need 4 hands. So like this expands on top and there's overlap while it shrinks on bottom, and then it expands on bottom and there's overlap while it shrinks on top. So this electron cloud is oscillating up and down above the plane of the molecule, and there's lots of overlap between the nuclei, and so it holds the nuclei together. So that's why we call it a bonding orbital. It's the side-on overlap of the p orbitals that makes it pi. It's the end-on overlap that makes it sigma. So these are p orbitals as well. This is the pz, on atom B, and this is the PZ on atom A, and there's end-on interaction that has rotational symmetry. And since it has the rotational symmetry, it's a sigma interaction, and it has that overlap, which provides lots of electron density between the atoms, so that makes it bonding. And up the top, there's no overlap, so when one's expanding, the other one is contracting, and so the node just moves back and forth, and that means there's less electron density between the nuclei, and so it doesn't hold them together. So we call that antibonding up here at the top. So this one's antibonding because of this node here between the atoms. It's sigma because it has rotational symmetry, and it's end-on from the p orbitals. Okay, so pi would be side to side on the p orbitals, and sigma would be end-on. And we get A1U from the character table. If we did the projection operator, the A1U row would have this combination come out the end of that projection operator. We would have a 2pz on atom A minus a 2pz on atom B. You know, as we do the rotation and the reflection and the inversion and all of that stuff, that row would produce this wave function. Yeah, yeah. Now you don't have to do the projection operator, even though I taught it to you guys. You could just say, I got 2pz orbitals, 2 of them. They could combine in phase or out of phase, right? And you know you have the sigma and the sigma star by the node that shows up, but you may not know the symmetry. And so then you might go to that last lecture and use that flow chart to say, if I go in the X direction, does it change sign? If I go in the Z direction or the Y direction? And so that's a way to kind of get the A1U and the A1G without the projection operator. Okay, so here's oxygen. And you can see the symmetries are on there. It's same symmetries as we had for fluorine. Okay. The only thing that's different with oxygen is we've got 2 fewer electrons. Okay. If you look at it, looks like oxygen is just 1 to the left of the fluorine, so it looks like we should have 1 fewer electron, but there's 2 of each, and so we have 2 fewer electrons. Where did we remove the electrons? So let me go go backwards. See, look here, we had 4 electrons here in the antibonding orbital. You see that? So if we remove, everything else is the same, but if we remove 2 of those electrons, we're moving them out of an antibonding orbital. And so the bond should get stronger, and it does. Oxygen has a double bond if we calculate the bond order. So the number of bonding electrons, I'll circle those. Or let me try to do symbols. I'll do a star. No, that's bad. Star is for antibonding. I'll do a triangle. Can we do a triangle? So the bonding electrons are triangles. Okay, I'm just figuring out an easy way to count them up. So I've got 2, 4, 6, 8. So I've got 8 of those. And then the antibonding we'll call stars. And so I've got a star here and a star there. So I've got 4 of those. So 8 minus 4 is 4, divided by 2 is 2, so a bond order of 2. No problem. So that's oxygen. Okay, here's nitrogen. Now nitrogen's a little strange. Okay, in fact, nitrogen, carbon, boron, beryllium, and lithium, all of those to the left of nitrogen and to the left are much smaller atoms. Okay, and since they're smaller, the electrons interact. There's some S and P interaction. Notice these down here. Look at this business. That looks weird, doesn't it? At the very bottom. Notice that it's not just a 2s, it's also a little bit of 2p. They have the same symmetry. The pz's and the 2s's are both top row. And so since they're top row, they can mix. Okay? And so this is the problem we have. So this is what we call lithium through nitrogen. It's called sp mixing. sp mixing. So we have all 4 of these orbitals mixed together a little bit. And that just changes the order. What's happened? This energy level right here in oxygen and fluorine was down here. but now it's up here. So it's moved. It's not quite as low in energy. Okay. But everything else is the same. You can see the pictures look the same. So these are all of the sigma interactions, and these are the A1G, A1Us, and then my EG and EU haven't changed at all. So they've kind of stayed put, but this energy level here, this 3 sigma G, has moved from below the pi bond to above the pi bond. Okay. So let's look at the whole second row. Okay, we can calculate this. This also shows a triple bond for nitrogen. I think that's a fill-in for your notes. 8 minus 2. So we've lost 2 more electrons out of this antibonding orbital. And so here's the whole second row. Now, we've gotten rid of the atoms on either side. So can you see that this is 1, 2, 3, 4, 5, 6, 7. So 7 MO diagrams next to each other. I mean, you could just draw your lines right here if you wanted to, to separate them. Can you see that? 7 individual MO diagrams. And so here's the symmetries, and we have that A1G level that moves quite a bit with the SP mixing. As if SP mixing starts to decrease, it finally drops down below the pi bond, the E1U level, when we go from nitrogen to oxygen. Okay. So these are the antibonding levels. You see those over there, the sigma star and a pi star. So if we're calculating bond orders, these are the electrons that we subtract. We add up all the bonding electrons and subtract the antibonding electrons, and we come up with the bond order. So here's our bond orders. So lithium would have a bond order of 1. So I don't know, is any Star Trek fans out there? Star Trek? It really goes way back, doesn't it? Yeah. They ran their ships on dilithium crystals. So this is dilithium. So I don't think we could run a starship on it, but it's pretty cool that dilithium exists. Anyway, science fiction. Good science fiction uses a lot of good scientific terms. Okay, but then we get to beryllium. This should predict that beryllium doesn't exist. So diberyllium should not exist because it has a bond order of 0. So we could draw a Lewis dot structure, but we could draw a structure from this, but it would have a 0 bond order. Then we get to boron. So diboron has a bond order of 1. Carbon, bond order of 2. Nitrogen, bond order of 3. Oxygen, bond order of 2. And fluorine, bond order of 1. Okay. Anybody have any questions about the bond orders? Now, there's lots of experimental data that confirms this, and one of those things is paramagnetism. So if we have a molecule that has unpaired electrons, then the electron spin, we call it spin, but it's really not spinning. What we're really saying is it has a magnetic field. So a spinning charge on a wire would generate a magnetic field. If it's spinning, if it starts this way and it turns left, it's spinning. Okay, and if it spins, then the z-axis is the magnetic field. So that's north. Okay, so a spinning charge would generate a magnetic field. And so we could measure the magnetic field of an electron, and we know an electron is a -1. And so we say, oh, this property is intrinsic angular momentum we call spin. I kind of wish they hadn't, because that implies in our mind a spinning thing. But what we really mean is it has a magnetic field. Okay. So if we have unpaired electrons, we have a net magnetic field. And so we should be able to measure that with a magnet, and we can. So we can measure and confirm that B2 and O2 are paramagnetic. So you can pour liquid oxygen between a magnet, and it will stay, like it'll get stuck between the magnet, because there's a magnetic field in the electron cloud around oxygen. So that's a really handy thing, because nitrogen, it's not paramagnetic. You see, it's diamagnetic. And so since nitrogen does not have a magnetic field and oxygen does, we could use that fact to separate oxygen from nitrogen. Now, I haven't looked, this might be something worth Googling, to see if that's how they do oxygen concentration. you know, my dad, when he was, he had problems with his lungs, and so he needed concentrated oxygen, and he had a little portable oxygen concentrator, and it would concentrate the oxygen and eliminate the nitrogen, and it was a tiny little box. It couldn't be some super huge thing, and so I wonder if it was using the magnetic properties of oxygen to increase the oxygen concentration. So that's a curiosity of mine. I'm sure Grok can tell me. So here's some more data that confirms the molecular orbital theory. So here's our bond orders up at the top and the theory associated with those. And this also predicts that He2 plus would exist. So He2 should not exist, but He2 plus should. And H2 plus should exist. And those both have bond orders of a half. Also, if we take an electron away from nitrogen, its bond order should decrease. But if we take an electron away from oxygen, its bond order should increase. So that's weird too. Just making a cation, you can't say if I make a cation, it's going to increase or decrease the bond order. You have to know the molecular orbital diagram, because nitrogen cation is a weaker molecule than nitrogen, but oxygen cation is a stronger bond than oxygen. So that's interesting. And it's because where are we removing the electrons? If we're removing electrons from an antibonding orbital, the bonding should get stronger. And if we're removing electrons from a bonding orbital, the bonding should get weaker. So that's the theory. Everybody's nodding their heads, I see, because you understand the theory of bond order. Look at the data. This is the bond energy. So if we're going to break that bond, it fits. It's not an exact match, but it definitely confirms the theory of molecular orbital theory. That the bond energy, so we weaken the bond we strengthen the bond by making oxygen cation, and we weaken the bond by making nitrogen cation. So that's pretty cool. And we see that He2 plus exists and H2 plus exists. This is bond length. So it's sort of an inversion thing. So like the triple bond is the smallest bond, and the single bond is the longest bond, and so we have nitrogen being slightly smaller than oxygen, and then smaller than fluorine, and then here's Ne2. So Ne2 should have a zero bond order. It has zero bond energy, but what's this? And He2 zero bond order, zero bond energy, but what's this? Do those bond lengths look like they follow the trend of the others? Really, what's up with those?
Almost like the inverse.
Well, yeah, bond length and bond order should be inverses of each other, but these are so long that they really don't classify as covalent bonds. They're just London dispersion forces or van der Waals forces that are holding these two atoms together. So they're really not forming a covalent bond. They're not sharing electrons. They're just interacting with each other. Okay. Now let's look at force constants. So the vibrational frequency, the spring that's holding these two atoms together, also tracks with bond order. So that's really great. So I would say the data confirms molecular orbital theory in terms of bond order for diatomics at least. And also, what would you do? Notice we never give this to the freshmen. If you're a TA and you're a freshman and you give them the Lewis dot structures, do the Lewis dot structure of HCl or something like that. We never give them C2, okay? I mean, maybe we do, but if we take that, we know each carbon comes along and it brings 4 electrons each, so we have 8 total electrons. 8 total electrons. We typically make a single bond between these two, -2 bonding electrons. We have 6 left. We start putting them on the more electronegative atoms. Since they're the same, we'll try to share them. 1, 2, 3, 4, 5, 6. So we've used up all 6. So we have 0 electrons left. And we try to get an octet rule for carbon, nitrogen, oxygen, and fluorine. So we're looking at this molecule, we're like, well, this one's got 6, this one only has 4, so let's share these two. Okay, so then we have this. Well, now each of them has 6. okay? Let's see, 2, 4, 6. And so we're going to share these two. And so now this carbon has an octet, but this carbon is still deficient. It only has 6. And so we're going to share these two. And so we have a quadruply bonded carbon atom, a bond order of 4, not an MO theory. Okay. And that would put this bond order up here, right? So that would be the prediction from our Lewis dot structure and the local bond theory. And that's not what we see here or here or here. So this data confirms MO theory, not the octet rule, not local bond theory. Now let's get into bigger molecules. So here's peroxide, so hydrogen peroxide. Let's, again, take it. How do you eat an elephant? How do you eat an elephant? One bite at a time. Right? So we got this big graphic up here, very confusing. Take it one bite at a time. Over on the left, what do we have? We have the symmetry adapted linear combinations of atomic orbitals. Hydrogen only has 1s orbitals. They can be in phase and out of phase. Do you have any questions with that? No. Okay. Over here, we have the symmetry adapted linear combinations of atomic orbitals for O2, the 2 oxygens in the middle. What does that look like? Looks like a diatomic to me, right? We've got the 2s orbitals in phase and out of phase, 2pz orbitals in phase and out of phase. We have the 2px's and 2py's in phase and out of phase. So on the oxygen side, can you understand that? Yes? Yeah. Now the symmetry labels are based upon this point group. We're just assuming that this has a C2H point group. So C2H point group. So that means it's planar. If you look up the actual structure of hydrogen peroxide, it's not exactly planar. It's twisted just a little bit. Okay, so it would be C2. It wouldn't be C2H. But I wanted it nice and pretty, so I made a C2H. It's just not the ground state. So then we can combine these, right? We use the symmetries to guide our combinations. So the A1Gs all combine with each other. So find all of your A1Gs. So here's an AG, or AGs, not A1Gs, just AGs. And so we have this AG. So this guy combines with these 4, or these 3 on this side. And so we come in with 4 symmetry adapted linear combinations, and those produce 4 molecular orbitals. So that's something you need to remember, that the number of orbital symmetry types are conserved. We come in with 4 atomic orbitals, we're going to end up with 4 molecular orbitals. This one, obviously, no nodes, lowest energy. Is everybody okay with this combination? All of them in phase. Okay. What about this combination? You see that the PZs can have the same shading on the outside here. And so we can just put the hydrogens in phase with that. Okay. And then here, this unshaded region on the PZ, on the PXs here, or the PYs, I don't know which, I'd have to look it up, can be in phase with the hydrogens. And so that, can you see this picture? Does that make sense to you as a combination of those two? Yes. And then this one here, this one right, it's this one right here that's out of phase. You see up here, we've got now a node here and a node there. Okay. So we should end up with 4 of these. We have this one, 1, 2, 3, and 4. Yes. A question? Okay. All right, great. So we could do this. I'm just showing you how we take the symmetry adapted linear combinations for larger molecules and then combine those. Okay. But what do we do with the bond order? So we need the number of bonding electrons for the bond order. Why is it not easy to identify? Yeah, what makes it hard to identify that because of that? Hmm? Say that again. It's polyatomic, but what is why? Which one of these is a bonding set of bonding? Let's just start at the bottom. Is this a bonding orbital? I would say yes. There's no nodes. Okay, so that's great. We'll do our little triangle thing. So I'm going to say the bonding orbitals are marked with a triangle. I just picked that arbitrarily. Okay, let's go to the very next one. Bonding or antibonding? Why do y'all say bonding? I see a node that breaks the oxygen-oxygen bond. Yeah. So you might be able to say it strengthens overall, it strengthens the bonding of the molecule, but it weakens the O bond. Yeah. So it's hard to say. So it's really not defined anymore. So this whole thing that we memorized with bond order only applies to diatomic molecules. It's very frustrating to a lot of people because they're like, but bond order is a thing. Yeah, it is a thing. It's very easy to identify with two atoms. And so that's how we have to talk about it. So for this one, I would say it's bonding for the OHs and antibonding for the oxygen bond. So you have to be specific. What bond is being strengthened, what multiple bonds are being strengthened, and which bonds are being weakened by this molecular orbital. Look at this one. This one is pretty clearly bonding, right? We've got nodes here on the oxygen atoms. So we have electron density between the oxygens. I could probably confidently say that's a triangle. This one too. That one's a triangle. This one for sure. There's no interaction with the hydrogens, so that's bonding. Okay. But here again, we've got one with a node in here. So that strengthens the OH bonds, but weakens the OO bonds. So who knows what that one is, right? And then this one is antibonding, so that would be a star. Okay. So we have some clear bonding ones, we have some clear antibonding ones, and then we have some that we really don't know. And so there really isn't a bond order that we can calculate for a polyatomic molecule. So you just put that out of your head. So the bond order and sigma star too, sigma star, pi and pi star is sort of halfway applies. Like this one for sure is like a pi star interaction because those orbitals are interacting side by side. But all of these others, like is this one pi or sigma? I would say neither. We don't have a term for that. Because it's side to side interaction on the oxygens, but in sort of end to end interactions on the OHs. And so we don't have a term for that. So we just leave it as undefined in terms of sigma or pi. Okay. So for polyatomic molecules, we still do have some clear pi interactions. Like this one right here is definitely a pi bond. Okay. And we have a pi star bond because it's just the p orbitals on the oxygen. No other atoms are involved. So that's clearly a pi interaction. Like benzene, we have those unused pz orbitals on the carbons. Clearly that's a pi cloud. So we can have pi clouds in a polyatomic molecule, but what about the px's and the py's on the carbons? We don't talk about the px's and the py's doing pi or sigma interactions. We just call the whole thing the sigma framework for the in-plane bonding on a benzene, but then the out-of-plane bonding, the pz orbitals, we would call those pi and pi stars. Okay, question?
Why do we call that non-bonding? Non-bonding?
Well, Yeah, we can sometimes identify non-bonding. Yeah, like in oxygen, in water, sorry, in water. The p orbitals, it's the x, so here's water, z-axis, x is coming out, and the plane of the molecule is the zy plane. So the p x orbital in oxygen doesn't bond with the hydrogens at all. So that any electrons in that p x are non-bonding. But these right here are bonding. This is definitely a pi bonding interaction between the oxygens, and this is clearly a pi star. So we wouldn't call those non-bonding. We would say they strengthen or weaken the bond. Yeah. But notice we don't have any lone pairs anywhere. Like there's no place where we have lone pairs. And in water, that px orbital would have 2 electrons in it. So it looks to me like water should be more like a trigonal planar, where we have the pz oxygen orbital interacting with the hydrogens, and so that's sort of the hybridization type mechanism, and then the only non-bonding pairs are in the px, and so we would say that oxygen, if we had to force it to be hybridized, losing a local bond theory, it would just be trigonal planar. So it would be an angle of 120, not 109.5. Okay, so this is where we are. Professors teaching MO theory love diatomics. Okay, and they neglect the other molecules. And then Charlie Brown is sad. He misses the days when bonds were drawn with sticks instead of this. Okay, and Snoopy goes, yeah, now we must look for nodes in the MOs, right, to determine what's bonding and what's anti-bonding. So you have to look to see, does this node, which bond does the node weaken? If there are no nodes, it strengthens all bonds. So this one is a bonding orbital, and there's 2 electrons in that bonding orbital, but they aren't associated with any single bond. It's a molecular orbital. It goes over the whole molecule. So even though this molecule orbital goes over the whole molecule, there's 2 electrons that are floating around over the whole molecule. Yeah. They're not associated with any particular bond. So the local bond theory, we could say at this point it's weakened. I wouldn't say it's disproven, but it's weakened from the data of the bond order in diatomics and the force constants, the bond lengths, and the bond energies. Local bond theory has been severely hurt. Okay, and we'll see that it's completely disproven in probably Monday's lecture. It might be Friday. Now, what I do for this, we don't have time, we have 2 minutes, but there's a poster outside that you can look at where we go through the full symmetry adapted linear combination of the hydrogen 1s orbitals. And so you can see up here, 4 of them survive if we go through the D2H character table. And these are the 4, the AG, the B1G, and so on. So these are the 4 symmetry adapted linear combinations of the 4 hydrogens around that molecule. Then we could do the carbons, the 2s's, in or out of phase. And we could do the px's, the py's, here's the py's, and the pz's, or x, y, and z. Yeah, these are the px's. In phase and out of phase. So we could treat the carbon-carbon bond like a diatomic with its orbitals. And so this is what we see. It looks very much like a diatomic energy level diagram for the 2 carbons. The 0 nodes, the 2s's in phase, the 2s's out of phase, the px's, py's, and pz's. So this looks just like the oxygen and fluorine diatomics. And then those are on either side. I just show you where all these come from. Now those are on the left and the right. So we have the hydrogen. We have the hydrogen 1s symmetry adapted linear combinations on this side. The carbon 2s and 2p's and so on, linear combinations on this side, and then we combine both of those to make the ethene molecular orbital diagram. So you can build these molecular orbital diagrams up from the atomic orbitals bigger and bigger and bigger. So I just show you, here's the AG interactions. So all of these four are AG, and they combine to make four in the middle. Then we have the B3Us that combine, and they make a bunch in the middle. And then the B2Us, and then the B1Gs. So then we end up with this, this middle piece right here, which is the molecular orbital diagram for ethene. Now, how many orbitals do we have with electrons? 1, 2, 3, 4, 5, 6. So we should have 6 energies if we were to hit this with UV light and measure the kinetic energy of the electrons that come out. Then we should have 6 peaks. If we were to measure the bond energy of this molecule with a local bond theory, how many different types of electron energies would we have? These are all identical, are they not? They're all CH bonds. So these should give 1 electron energy. So that's 1. Then the sigma bond would be 2, and then the pi bond would be 3. So we have 3 types of electron orbitals in the Lewis or local bond theory. So if we hit that with UV light and measure the energy of the electrons, we should have 3 peaks. So now we've got a testable theory. If this is right, we should see 3 peaks in the X-ray or UV vis photoelectron spectroscopy. If this is right, we should see 6. And so we'll leave that for next time. We actually do that experiment to look at the bonding.